Hey everybody, Mr. Stewart here, and welcome back to part two of two involving the probability involving sets. So in the first video lesson, you would have heard about mutually exclusive and non-mutually exclusive events, as well as independent events. And there was also some mention of Venn diagrams. Okay, now in this particular lesson, and as far as objective 3 is concerned, I'd like to share with you and have you think about the additive principle for counting, okay, as it relates to a couple of different problems, and also using Venn diagrams. So just as a quick recap, recall that when you have a variety of different problems, one of the key steps is to first decide which type of event or events you have. Okay, so in the first example where we had the roll of a die followed by the flip of a coin, we saw those as two separate events. Of course, the two of them, one not impacting the other one's outcome, and therefore we called those independent events. The second one, where we were rolling a sum of 2 or 12, we recognized that those values that make up the sums are not shared. Okay, so 1 and 1 and 6 and 6, by no means do they combine to form both 2 and 12. Okay, so we refer to those as being mutually exclusive. And lastly, rolling a pair, or that is doubles, or rolling fours, okay, a sum of 4, we saw that those were non-mutually exclusive events because they intersected here in terms of sharing that particular 4 is a sum of 4 as well as being a double. Okay, so today what we're going to do is take a look at some problems, 2 of them in fact, but before we do, I thought it might be a good organizer, actually, a great way to differentiate and to take inventory of the variety of different events. So on the far left we have, okay, so we consider any event. On the far left hand side we have what are called independent events, and for that we would use the multiplicative principle or the multiplicative counting principle. Under dependent, if we determine that there is a conditional, okay, so that the outcome of one event impacts the other, those are said to be dependent events. They're also non-mutually exclusive, but we'll look at those in the next section. Okay, but for now our focus is on these two here. So if it's mutually exclusive, we will be using the additive principle for what we call the union. So that is A union B, also known as A or B, is the sum of the two individual probabilities. And you can see below is a quick diagram that shows the disjoint sets and that they have no elements in common. So in the intersection of A and B, we have the null set or the empty set. They share no elements in common. Okay, and last but not least, we have what if they are non-mutually exclusive? That means that sets A and B overlap and that there are some shared elements or shared outcomes, okay, in a particular experiment. So up here we have the union of A and B. So the probability of A or B is not just the sum of the two probabilities, but we must also subtract out that which has been double counted. Okay, so as soon as the circles are overlapped, then the elements that are shared between A and B would end up being double counted and thus must be subtracted out. So let's move on and have a look at a couple of examples. Okay, so I think it best that we take a look through and that I would have you pause the video. So pause the video and then take a moment to process the values in the problem. See if you can assign them to the Venn diagram, and then we'll take them up. Okay, so in this particular example, we have a group of 70 people being surveyed Of this, let's see here. Yes, 70 say they read the newspaper online. Okay, and 83 are watching by TV. So 25 actually say they do both. So assuming they're involved in at least one activity, how many people get the news by reading or watching TV? Okay, so pause the video, and perhaps what you can do is assign one side, the pink side, to those who get news online, and the right-hand side to those who get their news by TV. All right, now that you've given that a go, let's see what we have here. Okay, so if A is the event of getting news online and B is that of getting it by TV, notice that in the central area, I have the 25 who do both. Now the 45 here, in terms of news online, these would be the people who only get their news online. Okay, and that's found by taking the 25 and subtracting it off of the 70 who say they do. Similarly, the 58, okay, are those who only get their news on TV. So by subtracting 25 from 83, we're left with 58. Okay. Now the question is, how many get news by reading or watching? So the number in A or B. So the number in A or B would be the sum of 45, 25, and 58. Okay. So as far as a formula is concerned, here's a representation of that. So the number of those in A or B, the union of A and B, is the number who get the news online, plus those who get it via TV, minus those who do both. Okay. Now the subtraction is necessary because otherwise we would end up double counting those 25 individuals. Okay. So it's important that they do get subtracted out. So you can see that had you calculated the sum of 45, 25, and 58, you'd get 128. And similarly, by using this formula, okay, it's also known as you might see this in other places. I'll shrink this down. It's also known as the principle of inclusion-exclusion. Okay, so you might see that referenced online or somewhere else. Okay, so we're using the principle of inclusion-exclusion, otherwise known as the additive principle counting. All right, moving on. Now, let's consider this one. Okay, so let's run through the same process. Okay, give yourself a little bit more time with this one, okay, before you press play to check things out. But this one here, we have 3 sets as opposed to 2, and the context is that of a game show. So we have contestants who are choosing a door behind which there might be a prize. And here are the results. 18 went with door A, 19 with B, 19 with C. 4 people chose both A and B. I'd like to be on that game show, by the way, to get more than one choice. 7 people choose A and C, and 10 went with B and C. And 3 chose all 3. So complete the Venn diagram and then determine how many got surveyed all together. So those that chose A or B or C. So pause the video, assign an event, okay, to each particular space that's here, and see if you can start placing some values into the Venn diagram. Well, welcome back. Let's take a quick look at what you have for values against this particular key. Now, take note, we're going to start at the center and work our way out. Perhaps you did the same. So the 3 people who chose all 3 go through the middle, okay, the intersection of all 3 sets. Now, keep working our way backwards. 10 people went with B and C. Well, the 10 people that chose B and C, okay, are here. So we have 3 already accounted for. That leaves us with 7. Okay, so in this space here, we would end up with the result of 10 minus the 3 yielding 7. Okay. Moving forward, take note that we do have 7 people choosing A and C. So that occurs over here. Okay, right here. And in that particular space, we would end up with taking the 7 individuals minus the 3 already represented, leaving 4. And as you can imagine, the remaining value, that is of the 1, results from the 4 people who chose A and B. So that 1 comes as a result of, the 4 people we're dealing with, minus 3 that are already accounted for, and bringing us to a grand total of 1. I'm just going to grab a digital eraser here and just correct my error. Okay, we'll go back to that. Doesn't seem to want to write. Let's try that again. There we go. Equal to 1. Perfect. So in terms of getting the number who are in A or B or C, that is the union of all of those sets, what we're going to have to do is to find the sum of all the values we found. Okay, so I'm not going to use any specific notation over here, but simply to indicate that we're going to find the sum of the 10. I'm just going to go around the outside here for now. So the 10 and the 5 and the 8. So those who do only those particular, or make those particular choices of A, B, C. And then we'll look at those who are choosing both. So we end up with plus 1, 7, and 4. And last but not least, I'll just drop down a line. And I'm going to add on the final value of 3, which comes through the intersection of all 3. So as a total, we should see roughly more than 30, I suspect. So we have 12 and 8 is 20, 35 plus 3, 38. So 38 individuals, that represents or is equivalent to the number of individuals who have chosen A or B or C. And using our notation, that's also equivalent to, so the union, so I'll just use the union symbol here, equivalently to mean the same thing. Okay, so that's one way to do it. There is but yet another way. So if we can represent it with a diagram, surely we can represent it with some form of numerical or algebraic representation. Okay. So we know, okay, there's a typo up there. I'm going to change that for everybody. I should read 38 based on our previous work. There we go. Much better. So based on that solution, we could also use the additive principle, or the principle of inclusion-exclusion, because we realize that the sets are not mutually exclusive. There is the overlap. So here's the relationship and some work that backs that up. Okay, so the formula, when you have the intersection of 3 sets, okay, or there are 3 events that are not mutually exclusive occurring, so we would add the elements in A, B, and C together, and from that we would subtract out the number in A and B, minus those in A and C, minus those in B and C, and then we add back in those who end up doing all 3, okay, and verifying that sum, okay, we end up with 38 individuals being surveyed. Okay, so I would strongly suggest that you do graphically organize your work in the form of a Venn diagram, okay, even so much more so than the formula, okay, because the formula conveys very little to no meaning, and that goes for any mathematics, without some other form, generally of visual interpretation, okay, and the visual can help support the development of formulas. So as you'll notice within your notes, there's a list of practice problems at this point in time If we're flipping the lesson, let's leave those problems go until we return to class, and we'll select those which might provoke some thought and to deepen our understanding as a whole class on this topic involving the probability using sets.